This lesson's title is Using the Theorem Part 2, and that might make you think I'm going to focus on the fundamental theorem of calculus Part 2, which I am. But that's not really why the title's like that. There's 2 lessons of talking about the fundamental theorem of calculus, which has 2 parts. And this lesson has 2 parts, so that's a little confusing. But that really matters. I'm going to show you some stuff. Yeah, here it comes. Using integrals to find areas. Okay, this has been looming. The last couple of days it might be like, oh, integrals is finding area. And the answer is, yeah, but there's some problems there, and we're now going to hammer those problems. There's been some things looming about positive and negatives. We're coming right after that right here. Anyways, it says, consider the integral negative 1 to 6 x squared minus 9 dx. Evaluate the integral. Well, I'm going to teach this like you barely know what's going on. Like you're way behind. You're like, I don't even know what this symbol is. And I'm going to teach it from that perspective. And if you're farther ahead than that, then you'll find this easy. The fundamental theorem of calculus, part 2, says, if you want to find an integral, which is some kind of area, and we'll get to the bottom of what that means, but for now I'll just describe it as the area under the curve. If you want to find the area under a curve for some function like that, your job is to find the antiderivative. Undo the derivative. And there's some tricks to handling that. I want to talk about that a little bit. When you see x squared, maybe the antiderivative just pops in your head. Or maybe just with a little bit of thinking you can handle it. But I'm going to try and do this question in such a way that it's like, I don't care what exponent's out there. It can be a fraction, it can be negative. My method's going to handle it. I go over and go, well, if it's x squared, the antiderivative must have had x cubed in it. I do that part first and get that down. That tells me that there's going to be a multiplier of 3 coming out of this. So whatever's out in front of here, I divide by that 3. So this is my guide as to what I put out front. It really makes it step by step. Write down the power, then take the power and divide whatever's out there by 3. And that makes perfect sense to me after doing it a bunch of times because I multiplied by what was ever out front when I did derivative. So now I'm going to divide whatever's out front. Then you can check it. You know, and I always do. Like in that next millisecond, my brain always checks it. I go, 3 times a third is 1 x squared. Very good. Try it again. Negative 9. Antiderivative of negative 9. Well, I need an x there to get back to a number. Then there's a 1 up there, so I go negative 9 divided by 1, and so I just get negative 9. And you might be like, well, I don't need that whole system for finding antiderivatives of constants. I can just look at those and get them. I'm like, okay, good. Don't use the system for those, but I just wanted to mention the system. Okay, back to my sentence that I started. The sentence I started was, your job when you're trying to find an integral is to first find the antiderivative. The fundamental theorem of calculus, part 2, says, find the antiderivative. Now, it was a long explanation. It was a long, scary explanation. And the first time through, I don't expect for a second that you're like, you could go up there and explain it to somebody where that all comes from. Scary stuff. But the end result was find the antiderivative and evaluate it at the 2 numbers there, the upper and lower limit of summation there, as we call them. And we have this new notation that if we put a negative 1 and a 6 outside the brackets out here, that means evaluate what's inside at both of these numbers. So it's shorthand notation. There are other ways to write it. Some books will write 1/3 x cubed minus 9x, and they'll draw a line here and deal with it that way. But that's sort of getting old school. You don't see that quite as much. You usually see it right outside the brackets here like that. But on the off chance you see a textbook with this, I wanted to warn you about it. So then, you sub in 6. So it's 1/3 6 cubed minus 9 times 6. That's the first evaluation. Then the second evaluation. I sub in the negative 1 into this bracket here. I've on purpose left this thing out in the middle here because I just want to talk about that in a second, what the fundamental theorem of calculus says. But I sub in 6 and I sub in negative 1. Again, you know, really bringing home why we did crazy subbing all these years. Seems like every single time we did algebra, oh, why don't you sub this in? Why don't you sub this in? Why do I have to sub in? Well, we got to get great at subbing things in, yeah? So I've subbed in 6, and I've subbed in negative 1, and then the fundamental theorem of calculus says you're subtracting those 2 things. Sort of feels like quotient rule, even though it's not really related to quotient rule, that you're doing a subtract in all this. Now, if you're heading off to a university that has a midterm coming up with no calculators. Those still exist out there where you have to be able to do these things in your head. That's why I still practice them. I want to be able to show you that I can do these things in my head if I wanted to. So 6 cubed is 6 times 6 is 36, times 6 is 216, divided by 3. Oh, that's 72. 9 times 6 is 54. Okay. I'm well on my way to handling this. And then this one's like a negative 1/3 plus 9. Oh, that's awkward. Okay, so 18 minus 8 2/3. Can I do that in my head? I think I can. 9 1/3. I didn't have to go to improper fractions there. I know how to do 18 minus 8 2/3. I first subtract the 8. That gets down to 10. Then I subtract the 2/3. Well, you can have your own fraction moves there. Yeah? Not going to get caught teaching fractions today. That's how you do it on the test or the exam or whatever. Now, when you're doing your homework, you immediately break out your fancy integral calculator and just pump that in to make sure you got the right answer there. Okay, so I'll move this over here where I can see. And so let's see, menu 1 for integrals. That's a math type thing. I got to be in math mode, so I go back to setup and I switch my calculator over to math mode, exit out of that. And so then when I go over to math and I move the arrow over, and again, if I'm doing any of that too fast, you immediately raise your hand and go, what? How are you getting to that so fast? You know, but hopefully that's stuff where you're like, oh, I know that's in there if I need it. And then I hit my integral button and I type in x squared minus 9 from negative 1 over to 6. Let's just see how I did. 9.333333. I don't know why I'm not getting fraction answers from my calculator today. I'll have to look at that in a second. But it's enough to make me go, yeah, 9 1/3, okay? All right, big moment. Any questions about that example? From the mechanical nature of this all the way to the idea, the big idea of how this all works. Maria. Oh, now that's a good question. I thought, I was a little worried when she raised her hand because I was like, is she worried about the 6 or the negative 1 or the antiderivative? No, her question is, what's the little dx here? What's going on there? 2 things. One is this dx is saying we're integrating with respect to x. That is, x is the important variable. And just like way back when we did dy by dx, and it was important to know before we took a derivative, what we were taking the derivative with respect to, because that changed what happened as we went along. If we were taking the derivative with respect to x, the derivative of x squared is 2x. But if you're taking the derivative with respect to t, the derivative of x is just dx dt. There's nothing we can do there, okay? And so this tells you that you're looking for x's inside there, which you're like, duh, won't it always be x's? No, no, there's some more to go here, okay? So that's one way to know what's going on. There's something else going on here. After all that Riemann sums nonsense, it's hard to understand. This is saying take the sum of the y value, which is the height of the rectangle, times dx, which is like the width of the rectangle. So that's all there in there, still laying there, and still with more to the story still coming. When we did this as a Riemann sum, this would have been delta x, the width of the rectangle. So that's still in the notation there, because we might need it as we go along here. Just like when Leibniz came along, dy by dx. You're like, why do we got to put the dx into there? And then later on, it was like, oh, the dx is so handy there when we're going to do other things. Okay? And that's going to happen more and more. Does that help? Yeah. For you, right now, the dx might just be, and you're using x as the variable. But there is more to what's going on here. This is a Riemann sum. It's a rectangle where you're multiplying the height by the width of the rectangles, and you're adding them all up. So all that stuff is still in there. It didn't get lost in the change of notation. Other questions? Next question. Does the answer from part A represent the total area between the graph of y equals x squared minus 9 and the x-axis? Explain. Well, my answer is maybe. It does represent an area. It does represent area under the curve. And it does represent area of the curve between the curve and the x-axis somehow. but there was this net area thing going on here, and it may not have been clear until I actually draw the picture and compare a bunch of areas to see what's going on. So I need a fairly good graph of y equals x squared minus 9. And it's no accident that I chose something that hopefully you're not blown away when I graph y equals x squared minus 9. You're not like, oh, where did you get the graph of that? Hopefully you're like, oh, I know y equals x squared minus 9. I know what that thing looks like. So here comes y equals x squared minus 9. Y equals x squared minus 9 has a y-intercept down here at negative 9. So I'll just label that on there just because I'm being careful. Turns out I don't really need that number, but it's important to get the graph and everything. And then it's a parabola that opens upwards like this. And I'm sort of unhappy with the way I drew that parabola. I want to give myself a little room to work there. Maybe it's not even clear why I had to change the picture there, but it just makes it so I can see what's going on here. Ooh, that side didn't look too good. I might have to, here. Ooh, there, that looks pretty good. Okay, even more important, let's get those x-intercepts on there. When is x squared minus 9 equal to 0? Okay, I could factor it, x plus 3, x minus 3. I could just bring the 9 over. I could do lots of things. But in the end, these two values here are 3 and negative 3. And just in that example, I made your whole grade 10 life worthwhile. Because we had no chance at this question until, we could just draw y equals x squared plus minus 9. Now, what we found was the area between, I forget what the numbers were again, negative 1 and 6. So we found the integral from negative 1, which is right about there, up to 6, which I'm just going to draw there. Okay, I know that's not really to scale, but it sort of gives you the image of what's going on here. So let me just fill this in with some, let's do some negative area here. See, it's down in there. See, that's all negative area. Well, no, it's not negative area. It's negative, and it's an area. When I go to the integral, these are going to come out to be negative, and it happens to be an area. And some math people just move on and say, I say negative area, you know what I mean. I know area can't be negative. When I say negative area, I mean area that just happens to be calculated as a negative value. Okay? Then, it also calculated, and I'm going to draw this area with green, this section over here, and it added up that area. And it added all that stuff up. Well, no, it didn't add all that stuff. It took this and subtracted this. So, now my maybe answer. I'm going to cross out my maybe answer and go, no. This was not the area between the x-axis and the curve. I'm now willing to say, no. It's a net area. That is, it's a area that's been added a whole bunch of positives and negatives and put them all together. And here's how I'm going to get around all the people that say you can't have negative area. I'm going to put the area with a little quote saying it's a sum of a positive area and a negative area. And when I added all those positive and negative areas together, what I got was, I forget already, 9 1/3. Making my diagram horrific. Yeah, because my diagram makes it look like there's a lot more in the negative than the positive, but that's not the way the actual areas came out, okay? Any questions about that? Like, why would we set up the integral that way? And I got to tell you, in applications, this is the way you're actually going to want it. If this was just about finding areas, we would try and do better than the way we set up the integral, probably. We would go, well, that's not very convenient. Don't we want something that finds areas? And we're like, actually, most of the game won't be about areas. These two sections will be, for you physics people, these two sections will maybe be energy and positive and negative energy. We do want to add them together because we want to find net energy, or it's net work, or whatever concept you're dealing with. So actually the way the integral set up is going to be better for just about everything else we do. But for particular areas, we got to do a little bit more work to actually get areas, okay? Determine the total area between y equals x squared minus 9 and the x-axis. Here's how we do it to find area. So here, area equals, so instead of doing the integral from -1 to 6, we're going to do the integral from -1 to 3. Just that part. Talk about that integral of x squared minus 9 dx. And I'm not going to put a plus or a minus here for a second here, because I really want to talk about what the heck is going on here. And then I'm going to do the integral from 3 to 6 of x squared minus 9 dx. And I've left out anything in between these two, okay? I'm going to come back and fix that. Like when you go to do them, maybe you're going to write something else in front of these things, knowing what's going on. But I'm going to approach it like I don't really know what's going to happen. I know I drew my beautiful picture and I went, I don't know what's going to happen. So really, it comes down to taking this thing and splitting it whenever you get a 0. Huh? Making advanced functions all worth it now. All that work to find zeros. Okay, we got to find the zeros of this thing and just integrate from one 0 to the next. And maybe we can do better and shorten this procedure as we go along here, and we'll talk about that as we go. So, but I'm going to do -1 to 3, up to the 0, and then I'm going to do 3 to 6, and see what happens in each of those sections. And now some review on integrals. To find these integrals, I have to find the antiderivative, 1/3 x cubed minus 9x, which, by the way, you'll get super good at all the basic ones. And I got to evaluate that between 3 and -1. And then I got to do an integral from, the antiderivative of the function from 3 to 6. I got to do those two things. Again, sort of bad form going on here down the center. I'm not writing plus, minus between them, anything like that. I'm just going to deal with them each separately because I really want to talk about it at the end, the results I get here. Then I get area equals, okay, so this first bracket will be, let's see, 1/3 3 cubed minus 9 times 3 minus 1/3 -1 cubed minus 9 times -1. And I've kept that in a square bracket this time because I'm trying to keep these two separate pieces separate so you can see what goes on here. 1/3 3 cubed minus 9 times 3, yes, minus 1/3 -1 cubed minus 9 times -1. Okay, and then something's going to happen here in between these two integrals. Yeah? I got to deal with that at some point. But over here, this whole integral comes out to, let's see, 1/3. Something's wrong? Did I write the cube here earlier and then erase it, or what happened? Or I was just talking. Yeah, up here, 1/3 x cubed? Yeah? Jeez. Just, whoops. Settle down. It's all right. I just pressed the wrong button. 6 cubed minus 9 times 6. Subtract 1/3 3 cubed minus 9 times 3. And I got distracted there, so I want to check all of this here. 1/3 3 cubed minus 9 times 3. Yeah, that's right. And that's all in a nice bracket there. Just going to make this bracket a little bigger. And then 1/3 -1 cubed minus 9 times -1. Yeah. And then over here, 1/3 6 cubed minus 9 times 6. Yep. And then minus 1/3 3 cubed minus 9 times 3. Okay. I don't know if you've noticed what I've done here. When I do nested brackets, I go a big bracket, and then when I'm inside, I do little brackets. It really helps me keep track of the brackets. Otherwise, I get myself confused about brackets there. So you might try some of that too. Some of the bigger and smaller brackets when you want to use those brackets. Well, okay, I'm going to nail down this whole bracket here. Let's see, 9 minus, let's see, 27. 1/3 of that is 9, and then that's minus 27. I think I get a -18 in there. Subtract, this other bracket is -1/3. Oh, that's awful. Plus 9, that's 8 2/3. And then, I don't know, something's got to go in between here. I don't know what's going to happen here. We'll deal with that in a second. And then this is, I remember this from the other one. This is 72 minus 54. And this is minus, I just did this one, so I can do it again and make sure it's right. 27, 9 minus 27, minus 18. And then, so this bracket I get negative 26 and 2/3. And this bracket I get 18 minus negative 18, I get 36. Okay? Let's just make sure that matches sign-wise with what I did before. The area from negative 1 to 3, sorry, the integral from negative 1 to 3 came out to a negative value. Is that what you would expect from the picture that we made? Yes, it's a negative area. It's an area whose calculation resulted in a negative sign. Then I did another area calculation from 3 to 6, and I got positive 36, which is what I would expect, positive type areas. And then, if I add those two areas together, 36 and negative 26 2/3, a negative, and for you physics people, a positive energy with some negative, some positive work with some negative work, of course, I would end up with a sum total of less work, 9 1/3. Well, that's not what I wanted to do here. I wanted to do area. So, two ways to handle this. Some people, if they know what the area is going to be, they just put a negative in front of this the whole time. And other people just go, well, I don't know what's going to happen here. I'm going to add these two things together, but I'm just going to put an absolute value sign around the thing and say, whatever you get there, just take its opposite sign when you get down there. I only want positives for my areas. So then this would have an absolute value around here, and I'm adding together with absolute value of this, and this would have absolute value, and I'm adding with absolute value of this. And this would have absolute value, and I'm adding together with absolute value of this. And then this now has an absolute value along with that. And so when I add those two together, I think I get 62 and 2/3. If I'm doing that in my head right. The absolute value of negative 26 and 2/3, positive 26 and 2/3, and add 36, 62 and 2/3. Any questions about that? It was a big problem looming. From the start of all of this, it was like, well, what about negatives? And this is the, well, simple. I almost used the word simple. After a whole page of crazy numbers, almost said simple. But the idea actually was simple. Find the areas between the zeros and just take the positive version of each one and add those together. We don't beat you to death with these type of questions because they're really not where we're going with all this. But do you have any questions about that? Steph? I don't know if this is what you mean, but the original question just said from negative 1 to 6, so I've sort of stuck with 6. Is that what you mean? Yeah, they're going to give me these two limits. And I guess when I actually get to do real world type problems, something about the nature of what I'm trying to do is I'll know what these two numbers, these two limits are, because I'll be going, oh, I only want to know how much did the work change from 2 minutes up to 6 minutes, or whatever, you know, something like that. Oh, yeah. Where's the constant, he says? Is that what you mean? Okay, if there's a constant here, and it's not if there's a constant. There is a constant here based on what's going on here. If I was to put that constant in there, this bracket here would have a plus c in it. That bracket would have a plus c, and that bracket would have a plus c, and when I subtract them, the c's disappear. So the constant's out there, living out there, but the way the integral's set up, the constants disappear. And that happens right in the fundamental theorem of calculus part 2 in the note. But again, you know, I was thinking about the integral and the snow falling off the front of the roof, yeah, out here. And they said it was dangerous. You're like, oh, snow falling off, it's not that dangerous. Well, it just depends on how much snow it is, doesn't it? Yeah? It's a few flakes coming off the side, what do I care? If it's a snowball coming off the top, what do I care? If 300 pounds of snow comes off all at the same time, I do care. And that's what the fundamental theorem of calculus lesson's like. 300 pounds comes at you all at the same time, and it's like, can I separate all the details? But the constant is dealt with in that thing. In the middle of it all, I find the constant right at the end. I go, what is the constant? The constant is f at a, and so it all plays out. So it's all built into there. But it's a great question. Those are really terrifying questions from the standpoint that you're not asking about, oh, what about the 3? What's 3 cubed? You're doing the right things like, yeah, I'll get all that worked out. I know how to do 3 cubed. I mean, even if I don't really see it on the board just yet, I'll work it out on my calculator. And you're asking the questions, really, what's going on? What's dx? Where's the constant in this? Really deep questions. Other questions here? It's another good question. Soon, instead of having little limits on here, sometimes we'll just have the integral symbol, and we mean to understand that that's just take the antiderivative. So yeah, we don't really have a special symbol that we need separately here, even though every time we take the integral, that very next line, what's in the square brackets, is going to be the antiderivative every time. And I need to tell you that we've really been careful about the antiderivatives so far. We've made them easy, or at least where I can talk you through them. Antiderivatives get impossibly difficult. Really, really, really unbelievably difficult. You can do a whole course just called antiderivatives. And they used to. Back when I went to university there, scared to come up with the number here, 1995. What year is this? 21? So 26 years ago, boy, first semester was just antiderivative, antiderivative, antiderivative. Nothing more than this every single time. A different function, different numbers in there. Let's try this one. Let's try this one. And it just got insane. So I warn you about that moving forward, that if you get stuck on antiderivatives for 6 weeks in your university course, yeah, they're tough. They're really tough to find them. The idea of what we're doing here is just finding the area under it. And real easy, the idea. Same as derivatives, right? Derivatives was like, okay, we're finding the tangent slope. I get it. Okay, now let's go do a bunch of derivatives. And product rule, quotient rule, tough derivatives, square roots, nested it. Like it just goes absolutely haywire, right? And that's what happens here too. Okay. Other questions here? 3 buttes, 3 great questions. However, let's get our calculator involved here and get a little help about what's going on, because the calculator can do some amazing stuff here. Did I do the calculator, do the original derivative? Oh, yeah, I did. Oh, the original integral? I did. Check this out, though. It's so good. Integral. Absolute value. See, your calculator can do something you can't do in the calculation. You just say, okay, take the absolute value every step along the way. Don't wait around till the end to find out if those areas were, quote, negative. If they're negative, make them positive right off the hop. And then go x squared minus 9x. And if you know how to type in here, please don't press enter just yet. If you've got everything in there, don't press enter until we do it together, because I'm actually curious about what's going to happen between your calculator and my computer. What was it, -1 to 6? -1 to 6. Okay? Now, I don't know how much processing power this calculator uses. I don't know whether it delves into the computer and goes, hey, as long as I got some power available, why don't I just reach in and use some of the computer power? Or whether it's an actual clone of your calculator and has the same computing power your calculator has, even though it's on a big computer here. You know, I don't really know. When we hit, did I do something wrong? Oh, -9. Good. Thank you for catching that before I pressed equals there. There we go. X squared minus 9 dx. When you press equals, watch what happens. All right, so press equals. Mine immediately came up with the answer. Does yours sit there for a minute? Oh, it's not a true ROM. It's using my computer's power to do computing. But is yours just sitting there going, do, and just sat there for a few seconds? Letting you know that whatever we did there just made this difficult for the calculator. It's like, okay, just a second here. Because it's got to go through and add up all the little tiny pieces. It's not doing what we're doing. We're like doing the algebra. The calculator just reaching down and sort of manually adding up every single strip. It's doing Riemann sums, which take forever. And so that's why it takes so long. Now, the one on the screen didn't, because it's got a Pentium 5 processor backing it up, where your calculator doesn't have all that, right? Oh, anyways, did I get the right answer? 62 2/3. I don't know why my calculator's not coming out with fractions today. I've obviously clicked one of the settings, or not clicked one of the settings, but it's enough to make me go, yeah, I feel pretty good about this. Okay. More questions there? So for us, we got to put the absolute values outside here and deal with it afterwards. The calculator can deal with it every step along the way because it's doing the individual Riemann sums in its little brain there. So here's the procedure. How to find the area analytically. To find the area between y equals f at x and the x-axis over the interval a to b, partition a to b with zeros of f. Find those zeros. Then integrate over each subinterval and add the absolute value of each of those pieces. I hope that's like, yeah, isn't that what you just did there on the board? Yeah, absolutely. Those are the instructions to do those. Not too complicated an idea. Obviously, the calculations have a lot of little steps in them. But your calculator's there. Even these little calculations in between, you could type just this in your calculator to double check your sum here. You know, there's lots of checks that you can do with your calculator to find out any little mistakes you found. So, next question. Use your calculator to determine the net area between the graph y equals x cos 2x. And here's a graph of it. Now, the fact that I've got when I first saw this, I'm like, isn't it obvious what the area is just by looking at this? And I'll talk about whether it's obvious what the area is in just a second. But I only put the graph here so you could sort of see what was going on. You don't really have the graphs. You don't really know what this area is going to come out to be. So, find the net area. So for net area, what we're going to do is, we're using our calculator. I'm going to hit that integral button. And the function I want is x cos 2x. And I'm going from -3 up to 3. And when I press equals there, I get area 0. Do you get 0 when you punch it in? Yeah, good that you're practicing with your calculator while we're doing it. Just talking to my advanced functions class yesterday. They watched me do it in the calculator, and that's not the point. I know how to do it in the calculator. You do it. Well, I'm doing it. Then compare it, right? All right. So now, before the start of this lesson, you might have been surprised by an area of 0. Well, that's not the area. That's the integral. The integral says if you take the positive areas and the negative areas and you put them all together, apparently that all ends up to 0. We're ending up right back where we started for you physics people. And there's the actual graph, which we don't know how to do at this point. We could get our calculator to do it. But you can probably see from that graph why that happens. Every positive area has a matching negative area. This is an odd function. And so odd functions will do this. If you take a symmetrical integral of an odd function, you get 0 when you come out of there. I'm not really making a rule there and warming you up for more learning. I'm just saying that's why it happened here. It says use your calculator to determine the total area between the graphs. That is, find the area part of it. How can I switch all of these little areas from negative to positive so I do get the actual area, the actual shaded in spot? What am I going to type in my calculator instead? Yeah, the absolute value, but inside. We can't put it inside like that, but the calculator can. So I'm going to go, I don't think you can fix this one. I tried another day and I couldn't really get it to go. So I'm just going to retype the whole thing in. Integral and then absolute value, which is right on the previous menu, right? If you just arrow over, the absolute value is right there. And then, I forget already, x cos 2x, x cos 2x. And we want from -3 to 3. Not 33, -3 to 3, x cos 2x, absolute value, equals. Did you see even my calculator hesitate? Because it's going, like, little delta x's, it's little tiny. It's doing like 1,000 subintervals, multiplying them all, the x's and the y's, and going through the whole procedure to think it through. Important thinking, especially for you computer people. I'm going to nudge a few computer ideas on later lessons. You're like, okay. So even if the calculator can do it, we still want the most efficient process. And you ran into this, you computer programming people before. You're like, I've got a program that can do it. It's just too darn slow to actually be useful. Well, not be useful, but it's just hitchy, you know? It probably happened to you if you have like a Samsung phone or something like that. It just It's not smooth, right? That's okay. I'm joking, but it's true. If you ever ran into somebody who's got like a $100 tablet at home or something like that, and you go to do stuff and you're like, what is wrong with this thing? Nothing. Yeah? But those Apple ones with even my old iPads, I got an iPad 1 and an iPad 2, and you're like, there's an iPad 1? Yeah, okay. So way back when, I got there's an iPad 1, and I go back to it now, and it just can't keep up. And so the calculations just aren't going along fast enough. They haven't got better at the calculations. All they do is just ramp up the speed of the hardware, right? But people who can write software that's fast are very valuable. I forget what we were doing. What were we doing? 5.425? Is that what you got? And then some other decimal places. And also I'll put area equals, and I'll put a little approximate sign there. And so the equation of this function on your screen here is y equals absolute value of x cos 2x. At this point, we're not good at evaluating absolute value integrals. The calculator can handle it. You're like, didn't you just do that? I'm like, not really. I just took the absolute value at the end. I didn't really take the integral of an absolute value. I took the absolute value of an integral, and you're like, what's the difference? Oh, it's a big difference. Yeah? I didn't go through each individual piece and decide if it was positive or negative. I just dealt with it as a whole thing there. The whole point of this lesson is that don't worry about the area thing too much. We can deal with the fact that it's not an area. For now, let's just focus on integrals, and if we have to go back and do individual little pieces of area, we can handle that really no problem. Yeah, it's not a big difficulty here. All right, well, if I put you to sleep there, you really need all your brain power right now, because this example, I nominate it as the toughest example we've done in any class anywhere along the way. This is going to stretch your brain. Simple answers, like the answers are, like the answers like 2, 5. The answers are simple, but the questions are really, really difficult. And you've got it in front of you, but I really don't like the size of this. So I'm going to go a lot bigger here, and I'll just have to scroll around as I do it. No, that's too big. 200%? Okay, that's good. Slowly. The graph of a continuous function f. This is f. Let me just label it on there, and I'll try and match the color too. Oh, that blue. I almost bought a shirt that was that color blue last night. Can you imagine if I was wearing that blue? Okay, you don't care. All right. As blue, there's blue right there. I'm going to label that f. How did I do in matching the color? Yeah? It needs to be clear what f is. That's the function f on the domain 0 to 8. So apparently this thing only exists between 0 and 8. Okay. On the left, let h be the continuous function defined by h at x equals integral 1 to x f at t dt. What? Here's what the h function does. The h function finds the net area of this function from 1, let me highlight that, from 1 up to some x value. Here, just imagine I made this a homework question. To really understand what h is, let's say I go and I say, Veronica, you do area 1 to 1.5. And Athena's going to do 1 to 1.6 and 1 to 1.7. Everybody's doing 1 to something. And you all get different answers because the area from 1 to 1.5 is different than 1 to 1.6, is different than 1 to 2, is different than 1 to 3. And h is all those answers. So you'd come back the next day, and h at 1 would be a certain value. H at 1.1 would be a certain area, a certain net area. H at 1.2 would be a certain net area. H at 1.3 would be a certain area. So h is just the, let me label that on there. No, not that color. Red for danger. A lot of thinking that has to go on here. This is a net area from 1 to some x value. Before I do h at 1, which actually is a very easy question if I've explained that right. Before I do h at 1 though, let's just talk about in general terms. If I did h at 4, would I get a positive area or a negative area? What kind of net area would I get if I went from 1 up to 4? positive. I hope I phrased that question well enough that you're like, oh, this isn't so hard. Why is he acting like this is going to be such a big deal? Oh, it heats up as we go along. Okay, so next question. What's h at 1? Emmett says 0, and he didn't even hesitate. He was like, whoop, 0. What is it about this that makes you go, oh, it's 0? 1 to 1. Yeah, so 1 to 1, if you're going, find the area from 1 to 1. So imagine, again, I gave this as a homework question. I handed out x values for you guys to find the area. And I went up and said, okay, Veronica, you do 1. Everyone in the class go, what? How'd she get to do 1? 1 to 1? Answer, 0. There's not going to be any area from 1 to 1. Yeah, is h at 0 positive or negative? Oh, I got to write it out. I got to write it out to know what's going on here. So whoever gets 0, the number 0, has got to do the area from 1 to 0 of f at t dt. They've got to go from 1 back to 0. Now, is that greater than 0? Or is that going to be less than 0 when they do that calculation? This is a really tricky one. Because your brain screams one thing, and then your brain tries to fix it, and then you doubt yourself, and it's good fun. Yeah? It's good fun on your brain. Causes your brain to do one of these. And challenge yourself here to really think about what you think the answer is. I did some reading on brain research over the Christmas, or the 26-week Christmas break I had there or whatever. And one of the things that is very interesting about your brain is the person who learns the most in the room is the person that doesn't quite understand what's happening. Yeah? When we take this up, the person that actually is like, I don't get it. Well, why isn't it positive? Why isn't it negative? And then when we give the answer, they learn so much. The person who gets the answer immediately learns next to nothing. The person who has no idea what we're talking about, obviously, learns very little. But the person who's right with you, struggling, painful, embarrassingly going, I don't get it, they learn a lot if they just stick with you. Yeah? So we encourage you to stick with us. Really try. I hope I gave you enough time to think this through. Is this integral from 1 to 0 of f at t going to be positive or it's going to be negative? His hand's up, and it's up and confident. It's like, yo, me, I got this. He says negative, and your brain screams positive. It's going to be less than 0. Let me just write that down. Will be negative. And I have 2 explanations, but I want to hear Brad's first. What's your explanation of why it's negative? All right, he's using the integral properties masterfully. He's just saying, well, I don't know. If I went 0 to 1, that's going to be definitely a positive result. So if I go from 1 to 0, I need to get the opposite result. Now, to go one step deeper than that, but why would that be true? If we went back to Riemann sums to try to do this, all the heights would be positive, but all the little delta x's would be negative because I'd be going this way every time with the intervals. Instead of going to find the intervals, instead of going 3 minus 2, 4 minus 3, 5 minus 4, I'm going 1 minus 2, 0 minus 1, and I'm getting negative values for all those little bases on the delta x's in the calculation. And so the calculation would come out to be a negative calculation. Tricky. And we're just getting warmed up. That's only b. Gets better. For what value of x would h at x be a maximum? Okay, let's see if we agree that as I make the x value bigger along here, we're going to be adding area all the way along there. That is, Veronica, h at 1, she's 0. H at 1.1, it's going to now be positive. H at 1.2, positive, still adding stuff. Still adding stuff, still adding stuff, still adding. We're adding area. For a long time, we're adding area. And at some point, we stop adding area. The area value stops getting bigger and starts to get smaller. Let's just make up some areas. Let's just make up some answers as I go down the rows. We get area 0, 1, 2, 3, 4, 5, 6, 5. Simon does his answer, and he gets 5. And Sal looks back and goes, how can you get 5? Mine was 6. He goes, because I had to subtract some area. You were at the max area. You had the most area. Then I had to subtract some area off the total. When does that happen? When do you start subtracting area instead of adding area? Maria? Yeah, h at 4 is a maximum. After that, we start, here comes my quotes, subtracting area. And it gets worse. Getting ready to answer other questions. After that, after Simon, it starts dropping. We start subtracting area, subtracting area. We're subtracting area the rest of the time as we go along there. Whew. It's a good one. How many more do I got to go? D and E. Okay, 2 more to go. D and E. Find the value for which h at x is a minimum. When do we get the lowest possible area? Will. X equals 8 sure feels right. It is so good. He says, okay, well, you're adding area, adding area, adding area, adding area, adding area, subtracting area, subtracting area, subtracting area, subtracting area, and then you stop subtracting area. And I'm going to write h at 8. And I'm going to put a question mark because I'm a little concerned about one little thing in all this. I'm a little concerned about whether it actually is a minimum or not. I like the answer, and I'd take it. In AP Calculus in high school, I'd go, yeah, I like it. But there's a little problem here about whether it actually is a minimum or not. Say it again. If you never add enough to go below 0, oh, okay, I know what you're saying. Can I add a word here? I'll put local minimum. Yeah, he's right. If we never add enough to go, we'll never get below that original 0. We may never get below that original 0. So when we say local minimum, we just mean it's one of those little bumps or humps. Now these definitions from advanced functions are coming back to haunt us. Local minimum, absolute minimum, endpoint, all this stuff going on here. And I've thrown the key word in there on purpose. What's the key word in all that makes us think that maybe it's not a local minimum? Veronica? It's decreasing, but it never increases after there. Decrease, decrease. We need to know what happens next. This is actually an endpoint of this whole thing, so we never know if it actually does that turn there. So as long as after h at 8 is positive. Oh boy, folks, I'm not warming up to hammer you with that on a test or an assignment. That's not really my intention here. But I do mention that we're not really sure that that's a minimum. Okay? Well, if that wasn't bad enough, the last one's a mind crusher. I got to find the x-coordinates of all points of inflection. Not this. Let's see, points of inflection on here would be not too bad. Where does it turn from concave up to concave down? We can pick those off, no problem. But points of inflection of h, oh boy. Wheels in already. Go. fx is the derivative of hx. All right. Let me just write out what he just said there. H at x is equal to the integral from 1 to x of f at t dt. That's what the definition was. We want to talk about the double derivative of h at x. That's what we really want to get to, and we've got a real mess here. We want to take h prime. That's what we really want to do. We want to take the derivative of this thing. Can we take the derivative of an integral? And the fundamental theorem of calculus, part 1, is sitting there going, yeah, I had to sit here all lesson. Let me in. Put me in. I can do it. I can do it. I can take this derivative. And I say, you can almost take this derivative. 1 to x, what were the rules there? How'd the video go yesterday? Did it play all right? It was all good. The fundamental theorem of calculus part 1 says if you're taking the derivative of an integral and the lower limit is constant and the upper limit is just x, and it heated up from there, right? It's like, well, what if it's not x? And then things got really wild. But this one's 1 to x. Then the derivative is just f with the x value subbed in. And if you haven't done a bunch of that homework, that is the kind of thing that will be on a test for me, where you have to apply the fundamental theorem of calculus, part 1. Hey, it's called fundamental theorem of calculus. So you just know it's going to be a fundamental part of your test. Yeah? And the examples from yesterday are sweet examples. They are the kind of stuff you really have to be able to do. Will went farther than he said, okay, well then that means h double prime is f prime. The double derivative of h is the derivative of f, and I can analyze the derivative of f. If I want to know where h double prime switches signs, I just want to know where f prime switches signs. So, points of inflection here will be max mins of the f prime. Where h double prime will be 0 is where f prime will be 0, is a much easier statement of that. So let me write that. Where h double prime is where f prime equals 0. So now I've just reduced this problem to finding out where the derivative of that original function equals 0. And when does it happen? Brad wants to take over. Go. 3 and 6. I want to mention one thing, okay? This question plays games a little bit. And the first time I ever saw this question, I spent a lot of time being worried about something all the way through. And I couldn't figure out what it was. So I'm looking through all the way through the question. I'm like, why is my brain screaming at me that something's wrong? Yeah? The original function says f has domain 0 to 8. And then it uses numbers lower than 1. And that messed with my brain a little bit. Because this 1 to x makes it feel like this function only exists from 1 to 8. But that's not true. It exists from 0 to 8. I just mentioned that because it messed me up when I was looking at it. By the time I was done the question, I thought we only went from 1 to 8. What that means is the max mins of f are x value x equals 3, x equals 6, but there is another max min of f in the middle of all this, and that's the x value of 1. By saying we're taking the integral from 1 to x, it made my brain believe that we were only looking here. But the function could have gone this way. And as complicated as this was, going that way is even more complicated. So I'm going to rest there. I'm going to say, okay, we delved deep enough into this question at that point there. But certainly more to think about there. Any questions about that one? Besides the fact that it just gave you a headache, like instant headache in the middle of all these. And it's the best thing for your brain ever. The reason these things are so good for you in math is that when you go back to actually, now after an example like that, when you go back to actually think about what the fundamental theorem of calculus part 1 does, and what part 2 does, and what does area, negative area mean, and the regular type questions, you're like, oh, I totally get that now. I might not totally get this, but I totally get some of the stuff that happened before that now. Okay?